Welcome to the 17th lecture in general topology. The topics that we will explore in this lecture include metric spaces and the metric topology. Okay, so in this lecture and the next we're going to be looking at metric spaces, which are very important to analysis. Very likely that these topics are going to be more familiar and certainly more intuitive than some of the more abstract concepts we've covered so far. So let X be any set a metric on the set X is a function which we'll call D, mapping the product of the set with itself into non-negative real numbers that satisfies three properties. The first property is called non-degeneracy. And by this we mean that d of xy is 0 if and only if x is equal to y. 2. The second property is known as symmetry. And by this we mean d of xy is the same as d of yx. And the third property is known as the triangle inequality. D of xy is less than or equal to d of xz plus d of zy. So the distance between x and y is less than or equal to the sum of the distance from x to z and then from z to y. The set X together with the metric D is a metric space. And the number d of xy is called the distance between x and y in the metric D. Okay, so let's quickly compare and contrast a metric with a measure. Now recall that a measure is a function from a sigma algebra into the non-negative subset of the extended real line, which includes the symbol infinity. So as it is a function from a sigma algebra, it takes as its arguments subsets of the underlying set, specific subsets, those subsets that are in the sigma algebra, and maps it onto a non-negative real number or infinity as a measure has as a codomain the non-negative subset of the extended real line. Now a metric is a function that takes two points in the underlying set and maps it into a non-negative real number, not inclusive of the symbol infinity. So the codomain is the real line. But again, this metric takes as an argument 2 points in the underlying space. Now they are similar in that both give us a meaning of size with a measure, we're looking at the size of a subset in the underlying set, and with a metric, we're looking at the distance, a measure of the distance between two given points in the underlying space or in the underlying set. All right. So let's look at an example. Again, let X be any set. The discrete metric on the set X is defined by d of xy. The distance between x and y is 0 if x is equal to y, and 1 if x is not equal to y. So only two possible values. Either if the 2 points are the same, then the distance, of course, is 0. Otherwise, if the 2 points are distinct, it has a distance of 1. Now, this is a function mapping 2 points in the underlying set into non-negative real values, so it is a candidate for a metric. To show that it is a metric, we'll show that it satisfies the 3 properties of non-degeneracy, symmetry, and the triangle inequality. Now, the first 2 are trivial. Very clearly, by the definition, the distance is 0 if and only if x is equal to y. And very clearly, we have symmetry. D of xy is the same as d of yx. So we need now show that this function satisfies the triangle inequality. So we'll look at the sum of the distance from x to z with the distance from z to y. And we see that this will take possibly 3 different values. We have the possibility of 0 if both of the distances are 0, that is, if d of xz and d of zy are both 0. The sum can be the number 1 if either the distance from x to z is 1 and the distance from z to y is 0, or has the value 1 if the distance from x to z is 0 and the distance from z to y is 1. And it has the value, the sum has the value 2 if both the distances are 1. That is, if the distance from x to z and the distance from z to y are both 1. Okay, so we need to look at each of these cases. So if the distance from x to z and the distance from z to y are both 0, then by definition, x and z are the same point. And from the second distance, we see that z and y are the same point. So we have x is equal to z, which is equal to y. And so the distance from x to y is 0. And this is certainly equal to 0. All right? So the next case, if the distance from x to z is 1 and the distance from z to y is 0, then as the distance from z to y is 0, this means that z is equal to y. And so the distance from x to z is the same as the distance from x to y, again because z is y, and we know this to be 1. And certainly 1 is equal to itself. So the third case rather, if the distance from x to z is 0 and the distance from z to y is 1, then because the distance from x to z is 0, we have that x equals z, and so the distance from z to y is the same as the distance from x to y, since x is equal to z, and we know this to be 1. And 1 is equal to itself. So in the last case, if the distance from x to z and the distance from z to y are both 1, then the distance from x to y is either 0 or 1, but certainly less than 2. And so in any case, we have that the distance from x to y is less than or equal to the sum of the distance from x to z with the distance from z to y. So the triangle inequality does indeed hold. And so as all three properties are satisfied by a function that maps 2 points in the underlying set into non-negative real numbers, it is a metric called the discrete metric. All right? So we'll look at another example. Let the set X together with some metric D be a metric space. Then the function rho, which is defined as the ratio of the distance from x to y in the metric D to the sum of 1 and the distance from x to y in the metric D. This new function, defined in terms of the original metric, is a metric on the set X. Now, this is a function that takes as an argument 2 points in the underlying set and maps it to non-negative real numbers, as the metric D will be a non-negative real number. And so this ratio is non-negative. So we need to show that this function rho satisfies the 3 properties that are, those properties are non-degeneracy, symmetry, and the triangle inequality. So first, notice that rho of xy is 0 if and only if d of xy is 0. And as d is a metric, we have that d of xy is 0 if and only if x is equal to y. And so rho of xy is 0 if and only if x is equal to y. So the function rho is non-degenerate. So next we check for symmetry. As d is a metric, it is symmetric. D of xy is equal to d of yx. And as rho is defined in terms of the metric D, we have that rho of xy is equal to rho of yx. And so the function rho is symmetric. All right, so now we need to show that the triangle inequality holds, and to do this we're going to use a little calculus. Let the function f be a map from non-negative real numbers into the reals, and let this be defined by f of x is equal to x over 1 plus x. Then the derivative is 1 over the product, the quantity 1 plus x squared. Now the test value, the possible critical value, is where the denominator is 0. This is at -1. And so as the function is defined, or the domain of the function is from 0 to infinity, we choose the test value that's in this interval. In particular, we can choose 0. At 0, this is 1 over 1, which is a positive number. And so by the first derivative test, the function f is strictly increasing on its domain. Now, as D is a metric, it satisfies the triangle inequality, that is, d of xy is less than or equal to the sum of the distance from x to z and the distance from z to y. And so we have f of d of xy is less than or equal to f of the sum Now f of d of xy is the function rho, which is less than or equal to d of xz, the distance from x to z, plus the distance from z to y, all over 1 plus the distance from x to z, plus the distance from z to y. Now, dxz over 1 plus dxz plus dzy is less than or equal to the distance from x to z over 1 plus the distance from x to z. And the equality can be strict if the distance from z to y is not 0. And the distance from z to y divided by 1 plus the distance from x to z plus the distance from z to y is less than or equal to the distance from z to y over 1 plus the distance from z to y. And this inequality also can be strict if the distance from x to y, or correction, from x to z is not 0. So we have two inequalities. So if we take the sum, we have that the distance from x to z plus the distance from z to y over 1 plus the distance from x to z plus the distance from z to y is less than or equal to the distance from x to z over 1 plus the distance from x to z plus the distance from z to y over 1 plus the distance from z to y. This quantity here is rho of xz, and this quantity is rho of zy. Now rho of xy is less than or equal to this term on the left of the inequality, and so rho of xy is less than or equal to rho of xz plus rho of zy. And so the triangle inequality does hold for the function row, and so the function row is indeed a metric on the underlying set X.